So again, welcome Jenilyn and Genevieve and Edward and Catherine and Eugene and welcome Braulio also. This is week 6. This is our, I think it might be our first Sunday evening webinar. Again, I take requests and whatever comes first is what, as long as I'm not teaching something else or something that always works. Oh, let me try something. I forgot, just a second. All right, can you hear me better? So I want to hear from you because I don't know. So does it sound better than it used to be? Okay, good. Yes. So let me show you what I was able to pick up. So I have this microphone and hopefully it works. It's a huge microphone, but certainly might work better. That's what I'm hoping for. That if I turn like a centimeter away, then it'll still hear me, unlike the computer. So hopefully that's going to fix the problem. So let me tell you the plan today. I'm going to share my desktop. Okay, so here's the plan. We'll start out with any questions you might have. And then after that, we're going to get into confidence intervals. This is probably the very first major statistical application that we're having in this class that is analyzing a sample to see how good the sample is. And confidence intervals will start out with for a mean. So that means that if we have quantitative data and we want to find out, we got the sample, and the question is how good is that sample? Okay, how good a predictor it is to the population. And then we'll interpret the confidence level. And we'll talk about that in a bit. And then we're going to do something that might confuse you a bit because we've kind of done it, but in a different thinking. So we've already talked about how big a sample you need to have a normal distribution. And that's nice because if you have a normal distribution, you can actually do computations. But even more importantly than that, you want a big enough sample so that you end up with results that you're happy with. Okay. And I don't mean happy as in you like that percent, but that you can say, well, I have results so that I know that there's a very good chance that my sample mean is going to be pretty close, is going to be very close to the population mean. Okay, which is different than saying you have a normal distribution. Okay, having a normal distribution just means you can do calculations, but really you want to say, well, how big do you want to be? How many people do you need to survey so that you end up with a sample mean that is reliable, okay, that you're comfortable with. So that's going to be a sample size computation. Then after that, we're basically going to do the same thing, except we're going to leave the quantitative question and we're going to move to the yes/no question. And we'll look into confidence intervals for a population proportion. So same idea. And then we'll interpret the confidence level. And then after that, we'll say, well, how big a sample do you need in order to have a sample proportion that you're pretty comfortable that it's pretty close to the population proportion. And that's what you want. So if you want to, survey all Americans about something, you can't survey everyone, but how many people do you need to survey? Okay. And not just NP and NQ greater than 5. That just tells you can do a calculation. Doesn't tell you have reliable stuff at all. Just says that you can do a calculation and at least the math is right, but it may not be very useful. Okay. So for example, for the mean, if I've said, I got my sample mean, height at 5'7", but I might be off by 3 feet. Okay, for the average American height. Okay, but I know my calculation's right because I can use the normal distribution. Well, that would be totally useless because if you're off by 3 feet in average height, you know nothing. So hopefully that makes some sense. So what we're going to do is we'll do Q&A. I want to mention something, and that is, what have you been doing either today or Wednesday or Thursday? I haven't looked yet, but hopefully all of you. My guess is some of you, it's very fresh in your mind. Discussion, yeah, but what's the bigger stressful thing? Yeah, the exam. Okay, yeah, there was a discussion, you're right, but the exam is what was the big stressful thing. So I want to let you know, I'll probably start grading it tomorrow, maybe the next day, because I also have to do the discussion post assignment to the grade. So then that's more relaxing, so I might do that first. And then I'll do the exam, but I'm not a procrastinator. So it's not going to be like a week before you get your scores back. It'll be pretty soon. Okay, I'll block that out. Yeah, the exam could be stressful, but it's important. Okay, it's very important. So I want to let you know that that I will get to it, but I try not to grade at night because I'm not a night person. I think I've told you that. So after this, you don't want me to be grading your stuff because I could make mistakes and stuff. It's not my best time at 9 o'clock at night or something. But morning, 6 in the morning, 5:30 in the morning, that's my good time. And then I'll start grading, and you should be able to see on Canvas what your grade is. And I write comments also. So if you get something wrong, I let you know what you did wrong. If you get it right, I don't feel like I need to write a comment, because if you get 10 out of 10 or 15 out of 15 and you got it right, I don't think I need to say much because you got it right. So just note that most of the comments are going to be things that you made mistakes on and what went wrong. So that's kind of the plan. So you'll be getting those comments as we go. Are there any questions about anything? Any questions? This is your chance to do it. Okay, if there's no questions, then I have a question for you, and I require you to answer it. But I want to remind you that when I say I require you to answer, it does not mean you have to give me an honest answer, but you probably are okay with an honest answer. It's one of my favorite things I like to ask as a survey because I think it's interesting. And broadly, I'm going to let you answer also, just because we need as big a sample size. We don't have that many people here, and this way we'll get more numbers. And maybe I'll even pop my number in too. Now, I'm not going to because I'm the instructor. So, and Braulio was, still a student just last year. So here's a question I have for you. Okay, and you have to give me an answer. And the question is, how old were you when you experienced your first passionate kiss? Okay, and you have to give me a number. Most of you will be telling the truth. If you don't want to tell the truth, give me a reasonable number. But again, no one's going to, do anything. And by the way, it's in the chat box. So your answer is not recorded. The numbers will all be recorded, but your answer is not recorded. Let me write it out. 16. And everybody has to answer. 18, 15, 19. 17. There's a reason I'm not answering, by the way. Okay, so we don't have too many. We don't have that many people here, but we do our best. It's much better when we have a bigger class for this. All right, so what we have is we have the answer to a survey question. And hopefully you all know that this is quantitative. So just to note that the answers, so how old were you when you experienced your first passionate kiss? Okay, and I will let you know a little bit why I didn't answer. Okay, I mean, I'll tell you, but I don't want my data to be in there because I don't fit in. And I'll explain. It's not because I'm weird, by the way, and I'm weird, but it's not. It's because I'm the instructor, not a student. So I'm in a different age category, basically. Okay. Again, I don't know all your ages. Some of you I don't have any idea because I've never seen your face, but you're students, so I know the average age of students isn't that high, like my age. So just let you know, I have been asking this question. I've been asking this question since I started. And do you guys remember how long I've been teaching statistics? And remember? $20 years, actually a lot longer, about 26 years was when I taught my first statistics class. So I've been teaching forever, which means I've actually watched society change. It's really exciting. Okay, interesting. Okay, and I'm not commenting good or bad, but there has been a change because I've been asking this question in every stats class since I started. So I've been watching it. Okay, what I haven't done is I got the numbers pretty much in my head, but not exactly, so I can't do full analyses later that we can do later in what's called regression analysis, which will be a chapter. Okay, so our numbers, by the way, 16, 18, 15, 19, 17. Okay, so the first thing, by the way, do we need to assume that the distribution is normal of the whole population in order to do calculations? What do you think? And if yes, why? If no, why not? And there is a why or why not. So do we need to assume it's normal? And if yes, why? If no, why not? And it should be pretty clear. Yeah, sample size is small, but how small? Right? We have a barrier in our class. Our definition of small. Yeah, not close to 30. I'm going to say it's not greater than 30. So since the sample size is just 5, then that which is, let me write down, which is less than 31, we must assume that the distribution is normal, the distribution of the population is normal. Otherwise, basically, we can't do anything. Is that clear? Okay, so we better assume the distribution of the population is normal. Otherwise, this is not even, it's just wrong in terms of what's coming next. Okay, let's do the following, and I'm gonna pop this in. And I'm not going to pop it into the calculator we're going to use in this chapter. I want to pop it in the old calculator because I want to understand stuff. So I want to just look at statistics. And this is definitely a sample. Let's calculate. Okay, the mean is 17. By the way, I'm looking at my paper when I'm talking. Can you still hear me when I do that? The mean is 17. Can you hear me? Okay, good, good. I got this new microphone, so I'm learning. I never used this thing until like just now. I did a little test this morning, but not with people, just in a recording. Okay, so the mean is 17. And what I care about, what is the other big thing we care about in this class besides the mean and the sample size? Yeah, standard deviation. Standard deviation 1.5811. Any questions on that? Okay, so what I'm going to do, let's write that down. And by the way, in terms of notation, what's the letter for the mean 17? It's very important. What do we use, or letters? What do we use for the mean of 17? What letter should we use? What's the notation? So pop in the chat box if you want, or say it. Okay, so be very careful. It's not mu, because mu is a population mean. That would be of all people, or maybe all students, if I'm thinking of students as a population, all college students in maybe California. Okay, mu sub x bar is a good try, but that would be all the possible samples, all the possible sample means of size 5 from groups of 5 students in California. And that's not what we did either. We just asked 5 people. So do you remember the notation to talk about this mean that is 17? Very important. Okay, so it's just x bar. So that's the notation to talk about a sample mean, is x bar. Got it? Again, we're going to be doing this a lot. We'll be looking at x bar, we're looking at mu, and you don't want to get them confused. And we'll look at mu sub x bar. So x bar is equal to 17. That was what the calculator told us. What's the notation for the standard deviation for these 5, for U5 in the sample? What letter? Do you remember? So what letter to use for the standard deviation for this collection of 5? Okay, it's not sigma. Sigma is a population standard deviation. That would be the standard deviation for all California college students. The hint is it's easy. Think English alphabet, exactly. What is it? N is for the sample size, but if we want the sample standard deviation, what letter? Yeah, it's S. So S is equal to 1.5811. Okay, and then what letter do we use for the number of people we sampled? We surveyed 5. So what letter is that? That represents the number 5? Yeah, that one's N. So it's very important you get the notation down. I'm going to be using it all the time for the rest of this entire class. We're going to, and when I say the course is what I really meant, we're going to be using this notation a lot. All right, so a few things. Really what we want to say is, well, we got this x bar is 17. So the question is, can you say that the average age of all California students when they got their first passionate kiss is 17? Okay, definitely not. You can't say that. We have a sample size of 5. Okay, we didn't ask everyone, but here's a harder question. All right, it may not be 17, but do you think it's unlikely that it's 11? That the average age is 11 based on what we've got here? Okay, so you're all saying it's unlikely. Okay, And hopefully you're looking at the standard deviation and noticing that, but we want to go a little farther because we also got to look at the n equals 5. So what we can do is we can look at sigma sub x bar. Now, here's an issue. Let me write this out first, though. So we're going to have sigma sub x bar and the central limit theorem told us how to calculate that. Well, that is sigma over the square root of n. That happened last week. Very important. Do we know how to get sigma over the square root of n? Do we know how to, put in numbers and get that number? Can we get sigma over square root of n based on what we've got here written down? Okay, and the answer is no. What's the reason why we can't? Yeah, we don't have not just answers, we don't have the population, we don't have sigma. Okay, we don't have sigma, so we can't just say we know sigma, so divide it by root n because we don't know sigma. But what we can say is it's probably approximately equal to the s over root n. And s is 1.5811, and n is 5. Any questions on that idea? Okay, 1.5811. Let's just pop it in. Divided by the square root of 5. And you get 0.707 about. Any questions on that? Okay, so now what we want to do is we want to say, well, here's the question. So the question is, how far off from 17 is the population mean likely to be? Okay, or more is unlikely to be. Actually, maybe how close to 17? Any questions on the question? Doesn't like my grammar. Huh. Any questions on the question? All right, so that's the big thing today is we're not going to say that the population mean is 17. We don't know exactly what it is, but what we can say is it's probably not too far from 17 because we have a sigma sub x bar that's kind of close to 0.707. Okay, the naive approach, and I'm going to do this because I think it's worth it, is to say, well, we have the mean of 17. We have sigma sub x bar approximately equal to 0.7. So let's draw a little picture. I think pictures are important. Okay, so let us go ahead And we are assuming we have a normal distribution. So that means I can draw a normal curve. Hopefully you all know that because that was a big deal in our class. That's part of the central limit theorem. So let me draw a normal curve. And by the way, oops, well, that last part wasn't so good. Let me try one more time. Yuck. Much better. Okay, it's not a perfect normal curve, but it's as good as I could do. So we got a normal curve. We know that the mean, at least the sample mean, is 17. So let's pop that in. That's about right. Okay, we know the sample means about 17. What we want to do is we want to say, well, how far off could it be from 17 and not be very likely to be farther than that? Any questions on that idea? So what I'm going to do is I'm going to draw that picture and say that the area there is pretty big. All right. When we say pretty big, that means you want to have a good chance of being right. Any questions on that? And in terms of your life, what percentage of the time are you comfortable being wrong? And don't tell me 0% because nobody's right always. What percentage of the time are you comfortable being wrong? Okay. Okay, so Edward said 5%. How about the rest of you? This is not a math question. This is a personal question. 10%, 10%, 5%. Okay. So this is something you have to choose. I'm going to mention a few things. One is the standard number is 5% chance of being wrong. Okay. For just general things that you want to like publish in a newspaper. So, which means 95% chance of being right. Because if you're wrong too often and you're publishing things in a newspaper, in a news article, what's going to happen? So if you're wrong pretty often instead of rarely, what's going to happen to your news station? You're going to get fired or closed down. People are going to stop trusting it and no one's going to watch your station anymore. Is that clear? All right. So it'd be nice to, maybe I'm going to say this is the confidence level, and I'm going to put in, instead of a number, I'm just going to put in CL. All right. Well, why don't we make the confidence level 99.99? What's the problem with that? Where's the trade-off? Because it'd be nice to be right almost all the time, right? 99.99% of the time. But what's the problem? Okay. It's actually not that hard to achieve. For example, on this question, I could be right pretty much all the time. But there's a trade-off. There's a problem with being right all the time. And it has to do with what I'm about to type in next. And I'm going to call this LB for lower bound. And I'm going to call this over here on the right-hand side UB. for upper bound. So the problem is, if you want to be right 99.99% of the time, what's going to happen to the lower bound and upper bound? What's going to happen if we want to really increase this confidence level to something big, like 99.9? You ask me far out, and what if the lower bound became 1 and the upper bound became 40? Well, then you're going to say, well, yeah, the average person has their first passionate kiss between 1-year-old and 40 years old. And everyone's going to look at you and say, and you're telling me what? You're telling me what's something I didn't know already? You know what I mean? So what you want is that distance between the lower bound and the upper bound to be narrow, but you also want the confidence level to be big. And this is the problem. You can't have both. Any questions on that? Okay. What's the only way to get a narrow width, but a high confidence level? It's the only thing you could do. Let's say you wanted to find out average age of first passionate kiss. There's only one way of doing that. Any ideas? Smaller age sample. Not quite. In fact, it's somewhat the opposite. So it's the only way is to make a large sample size. So instead of asking just 5 people, if we asked 500 people, then the standard error is going to go down by 10-fold. And then you could have both. But the trade-off on that one, what's the problem with surveying 500 people? What if I told you that's what you had to do for your project, for project 2? Survey 500 people. Yeah, difficult to do. Expensive, takes too much time, too hard. So there's all these trade-offs in reality. So you'd like a large sample size, but that's expensive and time consuming. You'd like a very large level of confidence, but that has that trade-off of making your lower bound and upper bound far from each other. But maybe you can make your lower bound and upper bound close to each other, but then you got to say, well, then I'm okay being wrong 40% of the time, and that's not okay either. So there's a lot of trade-offs here. Okay, any questions on that idea? Okay, so I want to mention something. I want to show you this picture, and then I'm going to show you the picture's not quite right. And the problem is, if we went and used the normal curve calculator and got these numbers, let's say we want the confidence level to be 0.95. Because that's kind of standard. We could actually use a normal curve calculator and get the lower bound and upper bound. Do you all agree you know how to do that, I hope? Hopefully, because you were tested on it. Given the standard deviation, I mean, but there's a very subtle issue here. And let me go back. Let's save. And the subtle issue is right here. What's the problem right there? Yeah, it's approximate. So there's more error because we don't know the population standard deviation. So here's a question which I'm pretty sure you'll have no idea the answer to. What does this have to do with beer? As in drinking beer, booze. Any ideas? Okay, and I'm not going to give you much time because you're not going to know. So let me tell you the story. The story was 100 years ago or so, they did it using the normal distribution. They did the calculation they didn't have calculators, so they used tables and stuff like that. And then there was this guy who worked in a beer company, and he did research on beer, and he realized that it was always off. And what he did is he came up with some very intense mathematics. And he worked in a beer company. He was also taught, by the way. He was also a math professor. And he did some very, very tough mathematics that even Braulio couldn't handle today, just let you know. And Braulio knows a lot of math. And came up with the exact answer instead of an approximate answer. Okay, up to the amount of decimals in a calculator you can put, but at least formulas for the exact answer. So let me write this out, and this is important. So to make these calculations, when we don't know the population, which you never do, standard deviation, but do know the sample, standard deviation, and sample size. And you always know those if you're taking a sample because you have your data. We use what's called the student's t-distribution. The professor that came up with this decided to honor his students by naming it after him. Okay, so this is called the student's t-distribution, and it looks somewhat similar to the normal distribution. There's it's a little bit off, but it's pretty close. And if the sample size is over 30, it looks exactly the same. Even at 15, it's almost the same. So that's the good news. Okay, but if it's small, like 5, it may not look the same. Any questions on this idea? Okay, and you could be glad the math is hard because that means you don't have to care about it. But you have to trust me that it works, or trust, the guy who came up with this. Any questions at all so far? All right, so now what I'm going to do, now I'm going to go back to the calculator. And now we're going to use the confidence interval for a mean with data. So to use this calculator, which I programmed, you can copy and paste the numbers separated by commas. So we had 16, 18, 15, 19, 17. We have to choose our confidence level. And how about 0.95, because that's the standard one. And I should hit calculate. Okay. I tried to make it easy. Did that look easy, by the way? Okay. And watching me is not the same, but I've heard it's pretty easy. That those of you guys who are using it, the feedback I heard is haven't heard any issues. All right, so what we have, and I use the letters LB and UB when I drew the graph, but that's lower bound and upper bound. And we have about 15 and 19. I'm going to go even one decimal place. That works. Any questions on using the calculator? Okay. All right. And again, are there other calculators you could use? Yes, but not on the exams. Because on the exams, I embedded in, as you saw in the first exam. All right. So now let's go ahead and take a look. So first thing, our confidence interval was from 15 to 19. And by the way, I did not plan the numbers to be so beautiful. Usually get really messy numbers. And here, this is even good to a whole decimal place. So this is like total luck. So good day today, I guess. Any questions so far? Okay, so now let's write our conclusion. Okay, and this is something I recommend getting a paper and pencil because you need to practice writing. Or even better is, popping up Microsoft Word or whatever you like to use and start typing, because that's what you really have to practice for the test, is everything's typed. So with 95% confidence, between, actually, let's write this down, the population mean first passionate kiss for, I'm going to write California college students, occurred between 15 years and 19 years old. I want to mention something, and I've done this before. Those words have to be there. When else did I tell you words had to be there? In another chapter. Do you remember? I've said it before. Yeah, that was the close to, and that was the expected value. Okay, good. Many and average. So now we're in a different set of words for confidence intervals. And this is how you start with 95% confidence. They always start that way. I mean, it could be 90% confidence, but the point is, it's the first word is with, and that gets you started. And then you must refer to the population mean. This is not, we're not saying we're 95% confident that the sample mean is between 15 and 19. How confident are we that the sample mean is between 15 and 19 years old? Not 95. How confident are we that the sample mean is between 15? We're 100% confident. The sample mean 17, period. We got it. We're not estimating. We know exactly what the sample mean is. The population mean, we don't know. Okay. And again, by the way, and we've seen this before, we have to assume in this case, because n is not greater than 30, that we have a normal distribution and an unbiased sample. Everything you do has to be unbiased. Okay. So for example, what sampling technique did I just use? Hopefully you know, because again, you were tested on this kind of stuff. Yeah, this is convenience sampling. I just asked you guys because you were easy to grab at the time. That's totally convenience sampling. So I want to let you know, don't trust this confidence interval for anything. But it's a good way of showing you how confidence intervals work. But I want to let you know there's some big problems. Convenience sampling in a sample size of 5 is never good. Any questions on this? Just a note, since this is what we got, How old do you think I was when I had my first passionate kiss? And I will tell you something before you guess. I was late. I was much older than anybody around me. Okay, at least a little older. So how old do you think I was? Okay, now here's the thing. You're obviously not my age. I was 13. And when I was in middle school, every 12-year-old was kissing. Life is different now. We had a lot more fun than you guys did. Tell you that. So just things were different. So culture has definitely changed. And I've been watching this for decades. So maybe, if you ever teach, 30 years later, people are going to say, oh, I was 28 when I had my first bachelor kiss, because it looks like it just gets older and older. Okay. So just let you know is that things have definitely changed. Okay. So, and I've noticed it. All right. Any questions on understanding this confidence interval? It's very important. I want to mention something else. Let's that's probably fine. The margin of error is the distance from the sample mean to the bounds. And the sample mean is always right in the center, so it doesn't matter whether you do lower bound or upper bound. So what is the margin of error now? Looking for a number? What's the margin of error? It's not a percent. What was the sample mean? It's up there in the picture. That's a hint. Sample mean was 17. Do you see that? And the upper bound is 19. And how far away from each other are they? That's not supposed to be a hard one. 2. So the margin of error is just 2. And often you'll say plus or minus 2. Two years. Any questions on that? Any questions? Okay, now I want to look at this picture again. And I want to think about it, about where all these numbers came from. Okay, this 95% is a probability. Okay, this graph, remember, is the sampling distribution graph. Okay, because we divided by the square root of n, remember, for the standard deviation. So the sampling distribution says that if you look at all the different possible samples of size 5, there's a 95% chance of being within these numbers. Do you see how that works? Another way of looking at it, instead of all, just say many, that's good enough, is that if many samples of size 5, of 5 college students, California students, are collected, then, so now we want to think about what this means. So then each of these samples will end up, just produce its own confidence interval. Okay, so if we asked a different 5 students, do you think we get the same mean and standard deviation? What do you think? So if we, instead of U5, if we picked a different group of 5, do you think we get the same mean and standard deviation? No, you'd get a different mean and standard deviation. You're asking different people. They're going to give you different answers. I mean, there's a very small chance, but basically no. All right. Well, if you get a different mean and standard deviation, then you're going to get a different confidence interval. Does that make sense? And the idea is, what do you hope your confidence interval contains? Right? You've published your paper, and what do you hope is true? What do we hope is true about our confidence interval, 15 to 19? We're not 100% confident. That we're not going to get. But what do you hope is true? If we publish that the average age is somewhere between 15 and 19 years old, what do you hope is right? Any idea? As soon as I say, it'll be obvious. No, we hope that the population mean age really is between 15 and 19. Otherwise, we've led everyone astray. Do you see that? All right. Well, we hope it's true. It may not be true. If you look at all the different possible confidence intervals you can collect, then 95% of them will make you feel good because it actually is true. So then 95% of these confidence intervals will contain the true population mean. Age of first kiss, passionate kiss. All right, and 5% won't. So I think I'm going to write in here. This is if I ask, interpret the confidence level. So if I ask you to interpret the confidence level, or if I said, what does it mean to be 95% confident? Then this is how you say it. There's no short way of doing it. If you think you could do it short, you're wrong. Got it? Okay. On the other hand, if I say interpret the confidence interval, that's this guy. Okay, that's your conclusion. So don't get confused between the interval and the level. Any questions on this? Okay, and you'll have time to practice. Okay, so quickly I want to mention something. All right. Do you think we had a large enough sample size? What do you think? Yeah, probably not. So here's the question. Let's suppose that the standard deviation is 1.58, because that's what we got, right? Okay, again, it's not exactly 1.58, but that's our best guess at this point. And we want to be 95% confident with a margin of error of, well, we don't want to be off by 2 years. How about no more than 0.1 year old or years? So we want to be real close for our average. Then we're real comfortable, and then we actually can say, hey, we know how old people are or were when they got their first passionate kiss for these students, for all students. So the question is, how many students need to be surveyed? Any questions on the question? Okay, I want to mention something. So the confidence interval, okay, goes by the following. We know that our margin of error, I'm going to use E for margin of error, is equal to the Z value times the standard error, which is sigma over root n. Okay, now in this question, what variable are we looking for? When I say how many students do we need to be surveyed, what am I asking for? N. So now comes the fun part. I know this is like all of your favorite things to do, and that is algebra. So I'm just going to quickly do the algebra in my head. And if you don't want to, you can just watch me do it in my head. So I'm going to multiply by root n, divide by e, and take a square of both sides. And what we get is n is equal to z sigma over e quantity squared. Oops. Ah. There we go. Nope. Okay, well, like the space is going to be there. So that's the formula for n. Okay, and I did something that made some other instructors pretty pissed at me. But my guess is you'll feel the opposite way. Is in our calculator. I created a sample size for a mean calculator, and it's going to do the work for you. So our sigma was, where is it? 1.58. Okay, I'm going to add the extra decimals too, 1, just because usually you want to have a little extra more decimals. Things get weird otherwise. Our E was 0.1. That was in the question. Our confidence level was 0.95, also in the question. And we get is 961. So we need to survey 961 college students. Any questions on that? Okay. Like I said, my friends, hopefully they'll stay my friends because they were a little upset when they saw this. We're not happy because they wanted their students to actually put it into the formula and, type out in the calculator. But I figured, I don't know, I'll let you do it this way. What calculated number? I don't remember the number. I remember it was the confidence interval for a sample size for a mean. I know it by the name, not the number. Yeah, number 11. Sample size for a mean. Okay. Any questions on that? All right. And by the way, do you think that'd be easy to do? Survey 961 college students? Yeah, no, that takes a lot of work. Okay. You're gonna have to spend a lot of money, paying people to do it probably. Okay. Or do it yourself, but it'll take you a year to do probably. I mean, take forever. And it's hard enough just to get a sample of over 30. Yeah. So just let you know, you look at this and you decide, well, maybe we'll let the confidence level be 90% instead, and then we could have a smaller n. Okay. Or maybe we're okay to being a half a year instead of 0.1 year. Okay. So you have to decide. Again, there's pros and cons of all different things. I will let you know that I do a lot of consulting work. Okay. Some I don't get paid for, some I do get paid. A while back, I did some consulting work for the Forest Service in Tahoe, and they wanted a 90% confidence level. So, I don't know if, hopefully you know this saying, the boss is always right. Have you heard of that before? So I used a 90% confidence interval level when I helped them out. Okay. And we worked it out. And the cool thing is, the last one I did was on how to make it so we don't have fires in Tahoe. And this summer, I know we got a lot of smoke, but it was great. So the statistics I did, I'm not saying I was the only one that made the difference, but I played my part in making it so that we didn't have a fire. Okay. I feel good about it. I'm not going to say that I was the one that made it, but I was a team player and I was a statistician to help them out. Okay, pretty cool. Okay, so statistics is used for everything. Any questions at all on this example? Okay, the next thing I want to do is move to the other kind of survey question. So what's the other kind of survey question where you don't get a number answer like we did here? Yeah, quantitative, and in particular, we're going to focus today and for a while actually on proportions, yes, no questions. So let me tell you what I've been up to about an hour for an hour and a half before. And do you recognize this? Yeah. So I'm actually voting. I'm about 2/3 of the way done. It's a long one this time, but it's definitely worth it. It takes a lot of research, but the question is, like right now, I'm voting. I'm getting close to the end, so I'm on the propositions. People are first. Propositions are after that on at least my ballot, probably yours too. And so the question is, which ones are going to win? Which ones are going to lose? So let me give you an example. So this is the Mercury News, San Jose Mercury News. And it says poll finds weak support for California gig worker measure with many undecided. So the massively expensive campaign for the state proposition let Uber, Instacart, and other major tech companies keep treating their drivers as contractors rather than employers remains wide open as election day approaches. All right. So the Berkeley IGS poll showed the side supporting Proposition 22, which has raised more than $180 million from 4 big tech firms eking out a narrow lead with 39% of the likely voters saying that they're in favor and 36% opposed. All right, I'm not going to read the whole article because we don't have all day, but I'm going to just focus on the 39% in favor. So do you believe that right now 39% of all California likely voters are in favor of Prop 22? What do you think? Okay, do you think they know this? Do they know that exactly 39% of all California likely voters are in favor? Okay, definitely not. How do I know for sure that they don't know this? My guess is you probably know for sure too, but I know for sure. Okay, now here's how I know for sure. Because they didn't ask me. If they knew all California voters, they would ask me. They don't know how I'm voting. You don't know how I'm voting. I haven't told you, and I'm not going to because I don't campaign. I only analyze statistics in class. Okay, I obviously I campaigned when I ran for office, but not in class. But here's the bigger question: how close do you think it is to 39%? Any questions on the question that I have for you? Okay, well, we have to do some work. So one thing is that if you click on the Berkeley IGS poll and you scroll down to the bottom, actually at the top, I think it said, I found it somewhere. Oh, maybe it was towards the bottom. Just a minute. There we go, about the survey. So if you want to look at the likely voters, 5,942 are likely voters. What letter is that? Yeah, that's N. Okay, by the way, is that a large enough sample size to use the central limit theorem? Yeah, very much so. Okay, even if it was only 20% of close to 6,000 is hundreds, right? Okay, it's even over 1,000. So we're talking over 1,000, and you just have to be bigger than 5 for the number of yeses and the number of nos. And there's definitely more than 5 yeses and nos if we're talking about, in the 30s%, even 40s. Is that clear? So definitely NP and NQ are bigger than 5. So we still need that. We're using the central limit theorem. Okay. Here's something we're going to have to figure out, and it's not hard, but we have to know how to do it. How many of the people they asked said yes? How do we find out? It's nowhere explicitly in the article, but we can figure it out. How many said yes? Okay, 39% is a percent, but how many people said yes? How do we figure that out? If you have to do a little math, it's not too hard, but you have to do a little math. I don't see y'all jumping in. It's not that hard. Okay. It would be 39% of 5,942. So in a calculator, you just go 0.39 times 5,942. Okay, so let me ask you, did 2,317.38 people say yes? No, that's not possible. No. No. 2,317 said yes. You can't have decimal point people. They didn't chop off someone's leg and then ask them and say, oh, now you're only, 0.7 people. Okay, so you always want to round, and you always need to round to the nearest whole number on this one. So 2317. Any questions on that? Okay, so come up with the, how about 95%? We could choose whatever percent we want. This is news. News is always 95% confidence interval for the percent of California likely voters who, and let's see, the 29%, 39% are in favor. Who are in favor of Prop 20, what number was it? 22. Any questions on the question? All right, well, let's go to our calculator. What do you think it is? What number? Yeah, it's 12. Confidence interval for a proportion. The N was 5942. The X was 2317. Confidence level, I'm using 0.95. Let me know if I'm going too fast. And here's the upper bound and the lower bound. So it's about, I'm going to round to the nearest percent, 38% to 40%. Okay, maybe I'll go one more decimal, 37.8 to 40.2. Any questions on the calculation? All right, now it's time to do what we did before, and that is write down the conclusion. With 95% confidence, we can conclude that between 37.8% and 40.2% of all California likely voters. Notice it's all, not the ones we asked, but every single one support Proposition 22. All right. By the way, based on this, do you think it is worth spending money to advertise? Right. By the way, in the article again, 36% were opposed. you think it's worth it? And the answer is yes. And the reason is if you look at 39 and 36, they don't add up to 100%. What does that tell you? No, these are likely voters. So people are going to vote or likely to vote. It's not that they aren't voting yet. All right. If you don't know, I'll tell you. It means that they haven't decided yet. They haven't done the research and figured it out. Okay. So that's why you advertise. You advertise to try and grab the people that haven't decided yet and say, hey, you know, this way's better. So it's definitely worth it. Had this confidence interval, had the numbers been both over 50%, then there's no reason to spend money. You got it. Do you see? But since they're less than 50% and there's a whole lot of undecideds, it's worth advertising. Any questions on this? And I will let you know another group I have consulted for was the California Democrat, the El Dorado County Democratic Party. And in the last election 2 years ago, I did their statistics for them. And I helped them understand what their people wanted and let them know who to endorse and why. So this stuff really is used, and I know it from personal, experience. Okay, so I've been involved in a deep way, not just teaching statistics, but actually lots of people need to use statistics, and that was one of my personal experiences. Is I did this stuff for them. Okay, and we don't have a lot of time, but it's a long story in terms of all the things I helped them with. All right, so let's continue on, and we can say that if many samples of 5,942 California likely voters are surveyed, then each one would produce its own confidence interval. Right? They'll all be basically different, pretty close to different. Now, what could we say about 95%? What do we know about 95%? Because that's what we're trying to interpret right now is what does this 95% mean? Any thoughts? I don't see y'all typing it in. Maybe you are. I'll type, but hopefully you type with me. 95% of these confidence intervals will contain the true population proportion of all Californian likely voters who plan on voting yes on Prop 22. Any questions on this example? Okay, the last thing I want to do is talk about sample sizes. Okay, so suppose we wanted a sample size. Oh, we wanted a confidence interval. And let's make it how about 90% just for fun? 90% confidence interval for the population proportion of all California likely voters who support Prop 22. If we want the margin of error to be no more than 3%, how many California likely voters must we survey? Any questions on the question? All right. Well, the good news is there's a formula for that one too. And because of time, I think I'm not even going to bother writing the formula, but you can trust me, there is. And actually, I think this one's worth it because we're going to have two formulas. So this formula is n is equal to p times 1 minus p times z. So z being the z value. By the way, if it's a 95% confidence interval, it's usually around 1.96. If it's a 90%, it's about 1.645, it turns out. So every percent has a different number, and the z distribution can help you with that. Z over E squared. One more time. That's better. Okay. So here we don't know P, do we? Or maybe we do. So the idea is if we use the 39% as our P, then we can plug it all in and get this out, or we can go back and we can do sample size for a proportion. So if we do have the estimate for P of say 0.39, that was our preliminary estimate. Maybe now we'll do a new survey because things might have changed. And then the E, we wanted no more than 3%. So you need to turn that into a decimal, 0.03. Confidence level, I wanted a 90% this time. And I can calculate N. Okay, and it's 716. By the way, if you wanted a 95%, then it's a little over 1,000. So it makes a difference. If you want a higher confidence level, you need to survey more people. Okay, if you want to have a strict margin of error of 0.03. All right, I got a question for you. What if you wanted to find out the proportion of college students who will take statistics? Okay. And let's suppose you wanted a margin of error of no more than 3%, and you wanted a 95% confidence level. Do you have an estimate for P? Do you know the proportion of college students who will take statistics? You have no idea. So if you don't have any idea, you can still do it. And it turns out that we have P times 1 minus P. What you can do is you can say, what P will make this the largest N? So it's kind of the conservative estimate for the sample size. And this turns out to be a parabola with vertex at a half. So it turns out P equals a half is what we use. But the way I coded it is if you just write no estimate, then it won't even ask you for P. It'll just give you P equals a half. And then if I calculate it, it's 1,068. Okay, and by the way, notice 1,068. Okay, that's a 3% margin of error with 95% confidence. It's pretty standard. All right, now do you see why I'm not going to ask you to do this for project 2? How come? Why would it be not nice of me to make you do this for project 2? What's the reason? Yeah, it's too many people to ask. I'm not going to make you ask 1,068 people. Do you see? So it turns out that if you're doing a mean, you often don't need that many. Okay, over 30, of course, but you don't usually need over 1,000. But if you're doing proportion, you usually need on the range of thousands, and that's hard. So just let you know, project 2, you're going to be doing another quantitative study, and the reason is so that you can have a sample size that's not evil. Okay, and I want to mention one last thing about project 2, because project 1 is over. So for your partners, the rules of the partners are you have to have partners. Okay, if you don't have a partner, you're going to lose 25%, which means basically you can't pass. So you have to have partners. 3 is better than 2, same rules, but you don't have to have the same partners. So if you got along really well with the 3 people that you're with, go for it. But if you weren't happy and you want to switch it around, go ahead and do that too. And just a note, I have a project 2 discussion forum, and that's where you post looking for a partner or 2 partners. Okay, right now, basically almost all of them, no one's posted anything yet because you haven't thought about it. But now is time to start thinking about partners. We don't have the math yet to talk about the project in detail, but I can tell you partners are important. So I think I'm going to stop the share. Oh, wait, one more thing. I'm still going to stop the share. I'm going to do it differently. I just realized, and you guys didn't remind me either. Just a second. I'll start the share in a second. There we go. That was it. Yeah, secret word. I was so busy voting that I forgot to grab your secret word and study it. So the secret word is all. Why is it all? Anyone know? Yeah, it's a keyword when you're interpreting the confidence interval, right? It's the population mean of all possible people. Okay, it's a proportion of all college students or whatever, or all likely voters. So that's why I use the word all. So now I'll stop the share. And stop the recording.